Hello, my name is Noah Abji, and today we're going to learn how to simplify fractions using the prime factorization of the numerator and denominator. So since we're talking about simplifying fractions, we should first review how to simplify fractions normally, which will also help us understand why prime factorization will be helpful in the future for simplifying larger fractions. So when we simplify fractions, we always find a common factor between the numerator and denominator, and divide both the numerator and denominator by that common factor. And remember, a factor is a number that something else is divisible by. So a factor of 4 is 2, for example, because 4 is divisible by 2. So let's do an example with simplifying fractions just to solidify it. Let's say we're going to simplify the fraction 10 over 15. So to simplify the fraction 10 over 15, we have to divide both the top and the bottom by the same number, right? So we need to figure out a number that both 10 and 15 are divisible by. Well, 15 is divisible by 1, 3, 5, and 15. And 10 is divisible by 1, 2, 5, and 10. Now, of course, they have 1 in common, but if we divide by 1, that's not going to change our answer. But they also have 5 in common. So let's divide both the top and the bottom by 5. And 5 is what the common factor is. See how it says common factor in our explanation. So we divide both the numerator, the top number, and the denominator, the bottom number, by 5. And we end up with 2 over 3 as our simplified fraction. So divide both the numerator and denominator by a common factor. All right, so let's look at another example. Now we have the fraction 30 over 96. So we're using a little bit bigger of numbers. Now immediately, because 30 and 96 are both even numbers, I know that they're both divisible by 2. So I'm going to start simplifying immediately by dividing both the top and the bottom by 2. Because for all I know, these might be the only numbers that they're divisible by that they have in common. So 30 divided by 2 is 15, and 96 divided by 2 is 48. So we get 15 over 48. Now, if you did a little bit more digging into these two numbers, you'd also find out that they are divisible by 3 as well. Now, here's a rule for finding out whether numbers are divisible by 3 that may be helpful in future. If you take the digits of the number, so using 15 as an example, and you add those digits, so we have 1 and 5, 1 plus 5. If it results in a number that is divisible by 3, such as 6, then the original number will be divisible by 3. For 48, for example, we add 4 plus 8, we add the digits together, and we get 12. And 12 is divisible by 3. So therefore, 48 is also divisible by 3. Even if we're to use a larger number, for example, 132. If we are to add the digits 1 plus 3 plus 2, we get 6. And since 6 is divisible by 3, 132 is also divisible by 3. So the way that I knew both 15 and 48 were divisible by 3 is that I added all the digits of the numbers, and I got that both of them resulted in sums that were divisible by 3. So therefore, 15 and 48 are also divisible by 3. So let's divide them both. 15 divided by 3 and 48 divided by 3. So 15 divided by 3 is 5, and 48 divided by 3 is 16. So now we have 5 over 16. And now 5 is only divisible by 1 and 5. But 16 is divisible by 1, 4, and 16. And since they don't have any other numbers in common than 1, this fraction is completely simplified to 5/16. All right, now let's look at one last example, 84 over 504. Now this is a really large number, and we could go through lots of steps to simplify, such as dividing by 2, and then dividing by 2 again, and dividing by 3, and so on, but that would take a really long time. And it's sometimes hard to figure out what numbers they share in common, and what we just did was really inefficient. Now this is actually just equal to 1/6, so we can simplify it all the way down to 1/6. But using prime factorization, we can do that a little bit more quickly. So for numbers like this is why we need prime factorization. All right, so yeah, we can use prime factorization to more easily simplify fractions. And we're going to go back to the example of 84 over 105 as I go through the steps. So remember, this is going to be equal to 1 over 6, 1/6. So let's go through the steps with simplifying with prime factorization to see how we actually get there. So of course, if we're using prime factorization, the first step is to find the prime factorization of both numbers. And so if you kind of forget how to find prime factorization, this can serve as a review for that. So when we find the prime factorization of any number, we find what prime numbers multiply together to get the original number. So the prime factorization of 4, for example, is 2 times 2, because it's only prime numbers, 2 and 2, that multiply to get 4. The prime factorization of 6, for example, would be 2 times 3, because we're using only prime numbers, which remember are numbers with only 2 factors to get 6. So we need to find the prime factorization of 84, and we do that using what's called a tree diagram. Basically, we draw branches from 84 and try to find 2 numbers that multiply to get our original number for each branch that we draw. So we need to think of 2 numbers that multiply to get 84. Any 2 numbers, it doesn't matter. And what immediately pops into my mind is 2 and 42, just divided by 2. So 2 times 42 is 84. Now, on this branch of the tree, this 2 here, since it's a prime number, we can't simplify it any further. But we can simplify 42. In fact, we can divide it by 2 again, since it's an even number, and get 2 and 21. Again, we can't simplify this 2, but 21 can be broken down into 3 and 7, because those are the only 2 factors besides 1 in itself. And now 3 and 7 are both prime numbers, so we can't break it down any further. So our prime factorization of 84, therefore, is all the prime numbers at the bottom of the tree multiplied by each other. So left at the bottom, we have a 2, another 2, a 3, and a 7. So let's write this out. The prime factorization, PF, of 84 is going to be equal to 2 times 2 times 3, and then times 7. All right, next, let's find the prime factorization of 504. And I'll erase this tree, but keep the prime factorization. So 504, and we can do the same type of tree diagram for it. So if we find the prime factorization of 504, let's think of 2 numbers that multiply to get 504. Well, it ends with a 4, so it's divisible by 2. So again, the first numbers that pop into my mind are 2 and 252. 2 and 252. 2 is a prime number, so it can't be simplified any further, but I can break down 252. So let's break that down further. Since it ends with a 2, we can divide it again, and you might have to end up using long division. Sometimes you can do this in your head, but this one's going to be broken down to 2 and 126. Now again, this 2 can't be broken down further, but since we have 126, which ends in a 6, we can break down 126 into 2 and something. It's divisible by 2. So this can be broken down into 2 and 63. All right, and so next, 63, since it's not ending in an even number, it's not divisible by 2 again. However, using our rule from the last slide, if we add the digits, 6 plus 3, we get 9. And since 9 is divisible by 3, that means 63 is also divisible by 3. So if we divide it by 3, we get 3 and 21. And again, 3 is not divisible or cannot be broken down any further, but 21 can be into its only 2 factors that aren't 1 in itself, which are 3 and 7. So we get 2, 2, 2, 3, 3, 7 at the bottom of the tree. So therefore, the prime factorization of 504 is going to be equal to 2 times 2 times 2 times 3 times 3 times 7. All right. So now that we found both the prime factorizations, and I know that took a little bit on this slide, But when you're doing it on your own, you'll get really quick at it, and this will be really quick, and so it's not going to take as long. So now that we found both the prime factorizations, we only have a few more steps to completely simplifying the fraction. So the next step is to rewrite the fraction with each number's prime factorization. So instead of writing 84 over 504, let's write the prime factorizations in the numerator and denominator. So for 84, let's write 2 times 2 times 3, and then times 7. And you'll see why I wrote it with these spaces in a second. It's because I like to line up where the 2's and 3's and 7's and 5's and so on are in the numerator and denominator. So for the denominator, the prime factorization of 504 is 2 times 2 times 2 times 3 times 3 times 7. So now we've rewritten our fraction with the prime factorizations. And the final step after we've done that is to cancel numbers in the top and the bottom. Now, since we're multiplying all these numbers in the numerator and denominator, there's something special we can do now. And that's that since we're multiplying, let's say, in both the numerator and denominator, we have 2's here. It's 2 times 2 times 3 times 7. And in the denominator, 2 times 2 times 2 times 3 times 3 times 7. We can just cross these off. They cancel each other out. And this only works because you're multiplying. If you were adding, you're not allowed to do this. But since we're multiplying, we can just cancel. We also have 2's here that we're multiplying, so these will get to cancel. We have 3's here that we're multiplying, so these 3's cancel. And we have 7's here that we're multiplying, so these 7's cancel. And since we have nothing in the numerator, it's actually just equal to 1. And in the denominator, all that we have left is 2 and 3. So we end up with 1 over 2 times 3. And when we multiply that all out, we get 1 over 6. And that's how the canceling and finding or simplifying fractions with prime factorization works. All right, so now let's do a review question. So if you'd like to try it, I'll give you a few seconds to pause the video before I go ahead and explain the answer. Okay, so the correct answer to this question was 5 over 7. So let's use our prime factorization method. So let's find the prime factorization of both numbers starting at 315. And I'm going to go through this fairly quickly now. So 315 is divisible by 5 since it ends with a 5 and can be broken down into 5 and 63. And next, 63 can be broken down into 3 and 21, which we remember from the last slide breaks down into 3 and 7. So the prime factorization of 315 is equal to 3 times 3 times 5 times 7. All right, next, let's find the prime factorization of 441. Now, since 4, 4, and 1, if we add the digits, add to 9, I know it's divisible by 3, so that's where I'm going to start. So 441 is divisible by 3, and I actually don't know what that's equal to off the top of my head. So I'm going to use long division to find what it is. So 3 goes into 441. So 3 goes into 4 one time. 1 times 3 is 3. Subtract, and I get 1. Bring down a 4. 3 goes into 14. 4 times 3 is 12. Subtract, and bring down a 2. Now the 1's here. 3 goes into 21 7 times. And so we multiply, subtract, and we end up with 0 at the bottom. Nothing left to bring down. So it breaks down into 3 and 147. So 3 and 147. Now this number may not seem special, but if we add the digits again, and I'm just going to erase this over here so we have a little bit more room. If we add the digits again, 1 plus 4 plus 7, we end up with 12. And since 12 is divisible by 3, so is 147. Now I can do this one in my head. Breaking this down is 3 and 49. So 3 and 49. And 49 can also be broken down into smaller numbers. If you know your square numbers or your times tables, you can break it down into 7 and 7. And there we only have prime numbers at the bottom of our tree. So therefore, our prime factorization of 441 is 3 times 3 times 7 times 7. Now, I've conveniently written these prime factorizations to easily turn it into a fraction now. So that's our second step. Rewrite the fraction with the prime factorizations in place. And now all we have to do is, since we're multiplying all these numbers, we can just cancel them. So these 3's cancel, these 3's cancel, these 7's cancel, and we're left with 5 over 7. So 5/7 is our final answer. That's all, and thank you for watching.